Okay, the formula for first order, or for any maximum of diffraction grating, is that d sine theta equals m lambda. Okay, so d is the separation of the lines. M in this case is first order, so m is 1. And theta, we're told, is 17 degrees. So d sine 17 is equal to m lambda, and the wavelength that we're using here is 532 nanometers. Okay, so when I solve for d, I get 1.82 times 10 to the minus 6 meters. And so the number of lines per centimeter, the line density, which sometimes we call that little n, is just 1 over d, and that's 5.5 times 10 to the 5th lines per meter. But the problem asks for lines per centimeter, so I'm going to take 5.5 times 10 to the 5th lines per meter, and then I'm going to convert to lines per centimeter. So that's 5.5 times 10 to the 3rd, or 5,500 lines per centimeter for the line density. Okay, now how many orders of laser light are visible in reflection? So there are a couple of ways to do that, right? One way is to set, d sine theta is equal to 2 lambda, d sine theta equals 3 lambda, and so on until theta is greater than 90 degrees, right? Until you get a sine theta that's impossible. But a different way to do it would be to say d sine 90 is equal to m lambda, and then solve for m. This will tell you which order will result in the maximum possible angle of reflection. Okay, so if I do that, if I solve for m is equal to, well, sine 90 is 1, so m is just equal to d times 1 over lambda. So that's 1.82 times 10 to the minus 6 divided by 532 nanometers, and that's 3.4. So that means 3.4 orders are visible. That means 3 complete orders are visible. Right? So that if I had done it this way, I could have gotten a theta for 2 lambda, I could have gotten a theta for 3 lambda, but if I try to set this equal to 4 lambda, it wouldn't have worked. So either way, I can get that answer.